Welcome to The Explainer. Today, we're diving into a paper that builds a bridge between two of the most mind-bending fields out there. We're talking about an ancient math mystery and the seriously strange world of quantum physics.
So let's just start with the big question. What on earth do prime numbers have to do with quantum physics? I mean, it sounds like a riddle, right? But the answer might just hold the key to $1 million prize, and maybe even a deep secret about how our universe is put together.
So let's start with one of the most famous unsolved problems in all of mathematics, the Riemann hypothesis. At its heart, it's really a hunt for some kind of hidden order in the complete chaos of prime numbers.
Okay, that definition sounds super complicated, I know. But here's the basic idea. Think of these zeros as special coordinates that literally map out the landscape of prime numbers. And what the hypothesis predicts is that all these crucial points, they fall in a perfectly straight, beautiful line. If you can prove that, you unlock some profound secrets about how primes are actually distributed.
Now, this is where things get really wild. Over a century ago, a couple of mathematicians came up with this idea called the Hilbert-Polya conjecture, and they asked a crazy question. What if this purely mathematical pattern isn't just math? What if it's actually the sound, the specific energy levels, being made by some real physical quantum object?
And that powerful idea leads us to this amazing analogy that scientists have been chasing for decades, the hunt for something they call a quantum drum. So this conjecture connects two totally different worlds. On one side, you've got this abstract mathematical pattern of the Riemann zeros. And on the other, you have the very real, quantized energy levels of a physical system, kind of like the specific notes that a guitar or a piano can play. The idea is, maybe they're the exact same thing. Okay, so here's the game plan. If the Riemann zeros are like a specific set of musical notes, then the challenge is to find, or mathematically build, a quantum instrument that naturally plays only those notes. In physics, the so-called instrument is called a Hamiltonian. Find the right Hamiltonian, and you could finally prove the hypothesis. Now, as you can probably guess, this idea is so compelling that people have been trying to design this quantum instrument for a really long time. But, well, the early models all had some pretty serious fundamental flaws. The most famous attempt is what's known as the Berry-Keating Hamiltonian. It was a brilliant, really elegant idea, but it came with one huge problem that just stopped it from being the final answer. See, the problem was that the Berry-Keating drum was basically a slide whistle. It produced this continuous smear of all possible notes. But the Riemann zeros are like the keys on a piano. They're precise, they're individual, they're separate. You need an instrument that only plays those specific notes, and the original model just couldn't pull it off. And this is where the paper we're looking at today comes in. A team of researchers decided to add a pretty radical new ingredient to the blueprint for this quantum drum, something called quantum acceleration. What they did was they took the classic Berry-Keating model as their starting point, but then they bolted on this new, complex part based on the idea of quantum acceleration. And this fundamentally changes how the whole instrument is built and how it behaves. This picture just illustrates the difference perfectly. On the left, you've got the simple, flat landscape of the original model, but on the right, that's the new one. The paper explains that this acceleration term introduces a curvature, and it's that extra mathematical bend that is the key innovation here. Now, this table from the paper shows that the new Hamiltonian is, well, it's a weird hybrid. It's something called non-Hermitian, which basically means it doesn't behave like a nice, closed quantum system normally would. And crucially, its ability to make those discrete notes we need is BC dependent. That means it's dependent on boundary conditions. In other words, its behavior totally depends on the environment you put it in. We'll come back to that. So, this all leads us to the million-dollar question, right? Does this new, more complicated quantum drum, does it actually play the right music? So this plot shows the notes, physicists call them eigenvalues, that the new drum plays. And as you can see, they follow this beautiful, really clear pattern. But there's a catch. The Hilbert-Polya conjecture says the notes have to be real numbers. They have to lie perfectly on that horizontal line, right at 0. These notes, well, they drift away from it. So to put it simply, while this new instrument is super interesting, it's not the final answer. It naturally plays complex notes, notes that have an imaginary part, when the whole theory demands simple, purely real ones. It's kind of like playing a whole chord when you're only supposed to hit a single key.
But, and this is a huge but, the researchers found something fascinating, which they say right here. They discovered that the instrument can be forced to play those discrete notes, but only if you do one specific thing. You have to put it in a box. Or in their words, you impose boundary conditions on a finite domain.
This is a massive insight. It suggests that maybe finding the right quantum instrument isn't enough. You might also need to find the right concert hall for it to play in. The physics of the drum could be spot on, but only when it's constrained in just the right way. So, what's the big takeaway here? Let's be really clear. This paper has not solved the Riemann hypothesis. Not yet, anyway. Instead, what it's done is it's forged this fascinating, powerful new tool for the search. It shows that by adding in new physics, like this idea of acceleration, the right conditions for those piano key-like notes can actually emerge. And honestly, it's just a beautiful example of how progress in science really happens, through these creative, brilliant connections between fields that seem totally unrelated, like number theory and quantum dynamics. And that leaves us with one last thought to chew on. If the secret to the order of prime numbers is really hiding out in the laws of quantum mechanics, what other profound truths about our universe are just waiting for us, right there at the intersection where different branches of knowledge collide?